Okay, so we spent the first 3 weeks of this class playing with chipboards, and I gave you these rules that said you have to use the same number, same color of chips on both sides of your picture. And then today, I give you these lovely professionally drawn pictures which violate everything we've learned up to this point in time. What you had today were window pictures. A window picture is a picture where the number of particles shown is impacted by the density of the substance, and this chipboard rule or conservation of mass rules are not going to be considered. It's really just another way to model a chemical process. We've been going with conservation of mass models. This is just an alternative model for looking at what's going on in a process. These pictures are going to tell you the types of particles involved in a process, and because they are in such common use in chemistry textbooks and also on internet sites about chemistry, we need to know how to read a window picture and then kind of translate it into our chipboard model for the purpose of doing some other things with it. So the focus for the rest of the day here is going to be on reading a window picture and redrawing it into a chipboard picture. You're going to need your periodic table as well as a calculator and then your lab sheet. The thing we're going to gain from a window picture is a feel for which particles are involved here. So we're going to start with this picture that's the magnesium burning with the Bunsen burner. So if we look at our window picture, the window picture here shows us that these particles are magnesium particles. So these are Mgs. Magnesium is element number 12 on the periodic table. So here's magnesium. We'll use its chemical symbol in order to label the chip. And this number down below tells you how much a magnesium chip weighs. A magnesium chip weighs 24.305 AMU. AMU stands for atomic mass unit. An atom is simply too small to measure its mass in grams, so chemists came up with a different unit of measure for doing the mass of individual atoms, and it's called the atomic mass unit. It's just kind of like if you needed to weigh a spider, you wouldn't use the unit of tons because a ton is way too large of a unit to measure a spider. If you need to take the mass of an atom, you wouldn't use the units of grams because a gram is simply way too large for measuring the mass of an atom. So there's our magnesium particles. The other window shows us that we have red particles, and according to the key, these are oxygens, except they come as pairs. And so the mass of these is going to be twice the mass of an oxygen chip. Oxygen is element number 8. It has a mass of 15.999. So this particle weighs 2 times 15.999 AMU. Or, if we get out our handy dandy calculator, those chips, or those particles, weigh 31.998 AMU. And this window shows us that the new thing formed is a combination magnesium, oxygen. And that combination is going to weigh 24.305 AMUs plus another 15.999 AMU. And so the total thing is going to be the sum of a magnesium plus an oxygen, or 40.304 AMU. So the window picture helps us identify who are the key characters in the story. Once we know who the characters are, we can draw a conservation of mass picture. So this was the one where you burned the magnesium strip. So I'm going to draw a smallish magnesium strip. And I'm going to use enough magnesiums that it kind of is going to look like a strip, but not so many magnesiums that I have to be drawing magnesiums for the rest of my life. Box it in to show that it's a solid. So there's a magnesium strip. According to my window picture, the magnesium strip is going to interact with one of these pairs of oxygens. And make the MgOs. So the window picture tells me what's happening. Is this an acceptable chipboard?
No.
No, this would not do well. I don't have an equal number on both sides. Okay, so let's use up all this magnesium. I've got to have 4 magnesium chips, and at the end of the reaction, there is MgOs. And I'm going to make it actually look like this. Like, it looks like we kind of alternate the magnesiums and the oxygens, so I'm going to draw the next one going the other way. Up on top here, MgO. MgO. And this stuff was a solid. This was the white junk that you dropped onto the little dish at the end of the reaction. Now do I have a good chipboard?
No.
No. What do I need?
More oxygens in the first one.
2 more oxygens, but luckily those come as pairs. And now my chipboard is good. Congrats. You just balanced your first chemical equation. That's actually what it means to have a balanced chemical equation, is that if you built the chipboard, you'd have the same number and color of chips on each side. Now we're going to apply the conservation of mass idea here, because we know what each of these chips weigh. We can chase the conservation of mass through here now. We've learned to chase conservation of mass as on the balance and off the balance. So, in the beginning, which pieces of this could I have confined to a balance in order to weigh it? The magnesium. So only the magnesium. Yeah. So that's 4 chips that weigh 24.305 AMU. Handy dandy calculator. 4 chips, each with a mass 24.305 AMU. On the balance in the beginning, according to my picture, would be 97.220 AMU. Off the balance is the oxygen. We just can't get those gas particles to sit on the balance to be weighed. So off the balance, I have 2 of the oxygen pieces, and each oxygen piece weighs 31.998 AMUs. So I've got 63.996 AMUs not on the balance here. And if I add up this mess, my picture has a total of 161.216 AMUs drawn into it. When we get to the other side of this mess, how much of this could we capture on the balance? All of it. You dropped all of it onto the little dish when you were doing the lab, so all of this is capturable. I have 4 of the MgO pieces at 40.304 AMUs each. And there's nothing left off the balance. So 4 particles at 40.304 AMUs each gives me 161.216 AMU on the balance, plus none AMU off the balance, for a total of 161.216 AMU. So what I've been doing with you with all these chipboard pictures is I've been teaching you to create a picture that follows the law of conservation of mass. Once you assign masses to all the chips, it becomes easy to see how making sure that you have the same number and same type of chips on both sides of your picture is in fact creating a picture that's consistent with the law of conservation of mass that governs the entirety of chemistry. So next week, kind of to review, we'll actually do number 5 in class. Let's go with a no homework for the weekend idea. And for our last 10 minutes of class, let's play a Gimkit to give you some practice with the elements and their symbols.